Hello again. It's Sally's turn this time. Mop hissed at me and took off in my last video. So this is part two of I'm not sure how many videos. And this is, of course, Sally with the white, the name's not very original, I must admit. Shackleton and Mop, great names. Sally, I mean, we're told this was a Sally when we got her, so we just stuck with that. So before I go into the discussions of the paleoclimate paper, the recent paper, I want to discuss what the Eocene was, and more specifically the Paleocene-Eocene Thermal Maximum, some of the characteristics of it. It was a very, very warm period in Earth's history, about 56 million years ago. So Sally's happy to take off, so let's get right into the Paleocene-Eocene Thermal Maximum. And remember, just a reminder that I've talked about proxies last video, so proxy evidence for the state dependence of climate sensitivity in the Eocene greenhouse. So I'm talking about the Paleocene-Eocene Thermal Maximum, the warmest period of the Eocene greenhouse. In this video, and I'll also talk about climate sensitivity next, and then we'll go into the details of the results of this paper. Okay, so this is the proxy data. I said there's different types of proxies, as I explained last video, and now the PETM. So about 56 million years ago, this period, it's one of the many episodes of global warming in the geological record, but there's still plenty of puzzles. So I'm delving into some of the important similarities of this time period and differences to modern climate change. So first of all, the continents were in different places 50 million years ago. So here's Africa and here's Europe. Europe's quite different. This is India here. And so this is the Africa-Europe view. And then if you rotate this way, India's here, and this is the Asian view, and this is Australia down here. So the world was quite different. The air circulation and water circulation were quite different. In this time period, there was almost no difference in temperature between the poles and the equator. Okay, so it was a very, very different situation. Very, very warm on the whole planet. Okay, now at the onset of the PETM, the oceans acidified in less than 10,000 years by around 0.3 pH units, so things became more acidic. The average surface ocean temperatures across the planet rose by 4 degrees to 5 degrees Celsius. Subsurface oceans warmed by 5 to 6 degrees Celsius. Ecosystems across the world were plunged into turmoil with poleward migrations, decline of reefs, extinctions of some sea bottom living creatures, and in some places 20% of land plants went extinct. Plant diversity dropped by more than a third. Okay, in mammals, there was strong natural selection for smaller body size to dissipate heat easier, high species turnover. There was no vertebrate mass extinction, though. The warming happened over a long period of time. Globally, the resulting climate of the early Eocene was up to 15 Celsius warmer than today, so there was lush vegetation supported on Antarctica and the Arctic. They were still towards the poles, but they were, of course, in different locations than they are today, and things, the shape of the continents and the ocean basins was very different. This all happened because of a geologically rapid release of 2,000 to 6,000 gigatons of carbon to the atmosphere. Now, modern emissions could reach close to 2,000 gigatons by the end of the century if we have business as usual emissions. But our emissions today are at least 10 times faster than the PETM emissions. The initial cause of the PETM is still debated, but there's evidence linking it to these huge volcanic eruptions at that time in the North Atlantic from Norway to Canada. So these eruptions would release methane and CO2 into the atmosphere, causing great warming. Right? You have underground baking of organic rich sediments by magma, molten rock, and then that would release the methane and CO2 in the volcano. And if confirmed, this would add the PETM to the list of strong warming events linked to these large igneous provinces, LIPS, okay, the heavy volcanic activity. Now, global warming. The latest papers confirm the global nature of the PETM warming by highlighting it in tropical climates like Tanzania, a mid-latitude location, Omsk in western Siberia, and many other locations. Shallow ocean waters reach temperatures around 34 to 36 degrees C, 93 to 97 Fahrenheit during the PETM, compared to today's values at the same location of about 28 to 29 Celsius, 34 to 36 Celsius. They must have had some zingers of hurricanes back then, fueling with the water temperatures like that. These PETM temperatures, they take into account the global ocean acidification, and it's a rise of about 3 Celsius from already warm pre-event temperatures. Okay, so it was a warm period in general, and then the temperature spiked. You know, most tropical plankton can't tolerate that. So they had to, so basically the temperature was lethal to plankton in the tropics. Tropical marine zooplankton migrated to higher latitudes to survive the PETM. Western Siberia was a shallow sea connecting the Arctic Ocean to the archipelago that made up Europe and Iran before the Himalayas and Alps were formed. Okay, sea surface temperatures rose even by a much larger 7 degrees Celsius from their already balming 21 Celsius. So the Arctic Ocean was basically 21 Celsius, and it rose during the PETM to 28 or so. The West Siberian Sea laid down a layer of black oily mud containing traces of green sulfur bacteria, so cyanobacteria, evidence of warm ocean-starved waters during the PETM. This is just an artist's conception, lush life in the Arctic during the Eocene 50 million years ago. Trees, lots of wildlife, tropics in the Arctic. Okay, there was a time lag of tens of thousands of years between the beginning of the event and the disappearance of plankton populations. Okay, and there's still mysteries on that. But the Siberian data show that the sea, and this is very key, this is very important, the sea surface temperatures were the same in the Arctic Ocean as a mid-latitude sea at 58 degrees north, some 3,000 kilometers further south. Fossil plants and animals show us the Arctic didn't freeze even in the winter. Other studies show the high latitude south, so Antarctica was also bizarrely warm. And it's hard for climate models to reproduce this lack of temperature gradient between high latitudes and the equator. Okay, almost no temperature gradient between the poles and the equator. I mean, this is what we're rapidly heading towards. The temperature gradient is reducing significantly. We'll lose sea ice soon. One summer, it'll take longer and longer to form. The duration of no sea ice will be longer and longer, and that will really have a huge impact, a huge abrupt system change to a new regime in the Arctic, and completely rewire our weather patterns. And I think it'll make it a real challenging period for humans to grow enough food to feed the planet. Okay, so the climate models just don't, they can't figure that out. They tend to simulate high latitude sea surface temperatures much cooler than the proxy temperature records tell us they were. So there's processes obviously at work to amplify polar warming that aren't captured in the models yet. Okay, and it's probably a rewiring of the ocean currents and the air circulation also. The jet stream, what would that look like? Does it exist? If there's no temperature difference between the poles and the equator, it may still exist if there can be a humidity difference. But it looked like the Arctic was lush and essentially tropical, so it's hard to say that there would be any jet stream. So land-ocean contrast would really take over. Many continents would have monsoon-like conditions, and you'd get stuck weather patterns with torrential rains in some regions and dry areas in other regions. The timing matters. How long did it take? There was a paper that said the onset of the PETM occurred in as little as 13 years. So that was in Clays in New Jersey. And then for 13 years, you'd expect maybe there was a comet exploding in the atmosphere, triggering the event. This paper's conclusions were demolished in a series of responses that say the heat capacity of the oceans required centuries to warm to the PETM event. An instant release of carbon would produce a carbon isotopic shift larger than that observed. Microfossils ruled out the sedimentary rates claimed. So we think it was spread out about between the emissions, the PETM emissions from the volcanic activity were probably spread out between 1,000 and 6,000 years. But now, so there was a 900,000, almost million-year period of elevated sea surface temperatures. A large rapid initial pulse of carbon and then slower gradual release of carbon. There's a lot more details here, but the key thing is that the change right now, okay, levels of CO2 in the atmosphere roughly doubled in the PETM. Okay, but we're increasing the CO2 levels at least 10 times faster than they increased during the PETM. Okay, temperatures rising by a PTM like 5 degrees Celsius in 3,000 years and gradually reducing over 23 to 165,000 years. So, if it happened, the PETM, the temperature change was a lot slower than today. That gave most species time to adapt, avoided ecosystem collapses and mass extinctions that the world has experienced with more extreme and more rapid emissions associated with these other end Permian, end Triassic, and other catastrophic times. So with the rates of change of temperature and CO2 now far exceeding the PETM, we won't have the luxury of having species having enough time to adapt. So just Google the title of this, The Perplexing PETM. It's on Skeptical Science, and have a look at that. Now, climate sensitivity is the last thing I want to discuss in detail before I go to that paper. First of all, quick thing, if you measure the boron isotopes, if there's a high pH, then there'll be a high amount of 11 boron, okay, one of the isotopes of boron. If you have a low pH in the ocean water, there'll be a low amount of the 11 isotope of boron compared to the 10 isotope. Now, high pH, okay, means that there's not much CO2, like less acidic ocean. Low pH, more acidic ocean, there's more CO2. Okay, so that's the key. That's the key thing, information from boron in the paleo pH system, if you like. And now, how do we estimate climate sensitivity? So, this is a great article. Have a look at it in detail. I'm just going to discuss a couple key things. First of all, there's equilibrium climate sensitivity. The Earth's climate takes time to adjust to changes in CO2. Okay, because the heat, for example, takes decades to disperse through the deep ocean. So ECS, equilibrium climate sensitivity, is the amount of warming that will occur once all these processes have reached equilibrium. And this is understood to be 1.5 to 4.5 Celsius with an average of 3. This transient climate response, or TCR, is different. If CO2 is increasing 1% a year, and when it eventually doubles, what's the temperature at that point? That's the transient climate response. There hasn't yet been a distribution of heat between the atmosphere and oceans to reach equilibrium. And there's a third sensitivity, Earth System Sensitivity, ESS. This includes long-term Earth system feedbacks, like changes in the ice sheets or changes in the distribution of vegetation and other things. Okay, so TCR is lower than ECS. ECS is likely between 1.5 and 4.5 of warming. That's for a doubling of atmospheric CO2 concentration, but the TCR is only between about 1 and 2.5 Celsius. And ESS will be even larger. And I just want to show you a couple things, but I'll do it in the next video. Thanks for listening.